is going to be about the encrypted supercomputer. So, what is the encrypted supercomputer? So, the problem on Solana or on any public blockchain is that everything is public, right? But you don't want to keep all of your data public. There are some things that are private to you and should be kept private. So, for example, if you want to offload some tokens, sell something or buy something, and you have an information edge over the market, if you do those trades publicly, then someone else can copy trade you. They can learn more about it, and you sort of start losing your edge over time. And that's why we believe that privacy is super important for public blockchains. So what's Arcium? Arciums is a stateless encrypted compute network. We use Solana for consensus as well as the state layer. We don't do any of that. All we try to do is to build the best way to have encrypted shared state on chain on Solana, such that anyone can write arbitrary programs which can execute any arbitrary computation in an encrypted fashion. And what that means is that your inputs and outputs both can be encrypted while not being able to be decrypted or to be seen by any single party alone throughout the entire computation lifecycle. So it's been a year since Arcium's been live. We previously built out one of the largest privacy protocols in Solana back in the day called Elusive. We saw that there were certain limitations with the infrastructure that we were building, and we saw that there was a better opportunity to build better infra such that anyone can build privacy preserving applications in Solana in a much easier fashion. We've built Cerberus MPC protocol, which is our core MPC protocol. On top of that, we've built Arcis, which is our Rust compiler, which can compile basic Rust programs into MPC bytecode without you having to know any cryptography, anything about MPC whatsoever. So you just write your normal Rust code, you add a few macros here and there, and we take care of everything else. We've shipped up public testnet. Yesterday, our public testnet V2 went live with over 15 applications deployed with hundreds of thousands of transactions. We've built out a demo of an encrypted order book on chain. So the entire order book is encrypted. No one knows who's trading what, but your orders get matched efficiently as and when there's an opposite order of the like. We've also acquired one of our largest Web2 competitors, Infer. They were backed by JP Morgan and a bunch of other banks. They've been around building FHE and other privacy infrastructure for over a decade. Yeah. So we've done a bunch of research on how Arcium does things. So we've published research on, I talked about Cerberus, but we also have Manticore, which is the world's most efficient MPC framework, which for supporting real number arithmetic. What that means is that it's extremely good at privacy preserving AI. We've also done research in FHE on how we could improve that, but our main priority remains in MPC. So why do we need privacy? So privacy is a core aspect of your day-to-day life. No one knows, except maybe some centralized authorities, what's your bank balance, who you're transferring to, what's going on with your finances. No one knows what JP Morgan is trading. No one knows what these big banks are doing. And we can't expect people, retail or institutional, to come on chain unless there is true privacy on public blockchains. So, for example, 60% of all daily US spot volumes goes through something that's called dark pools in TradFi. Dark pools in TradFi are basically custom order books built on top of exchanges like NASDAQ, Sensex, etc., which offer these institutions a way to offload their funds or buy without anyone else knowing that they place this order on the public market. So some centralized authorities like Citibank, Bank of America, they might be running these sort of like layer 2 order books, and you and the other institutions can trade on this order book, and only the remnant order which remains after some trading period gets placed on the public markets like Nasdaq, so that no one really knows who traded what. It's just some small order or something, the net order which goes on the public market. So privacy also allows us to build a new set of applications which weren't possible before, right? So for example, with gaming, we have never really had things like blackjack or poker completely be on chain. The reason being that your edge in that game is that no one else knows what your hand is. And if your set of cards are public on the blockchain, then there's no game whatsoever, right? Everyone can see what's going on. It's not of much use. So privacy allows us to bring net new applications on chain, not just improve the current set. So we like to categorize privacy into two different categories: privacy 1.0 and what we call privacy 2.0. Privacy 1.0 was mostly isolated. There was local state that was private to you, but no, you couldn't do shared state, right? So having your balance private is a local isolated secret state, but trading on a confidential order book is now an encrypted shared state, because you're not the only one who has access or can interact with that piece of state. There's others who's placing orders as well. Whereas with your balance, only you know what your balance is, only you can spend it. No one else can actually modify it. So privacy 2.0 allows us to do a lot more powerful applications than what were historically possible. Yeah, some of the applications include private DeFi, not just private transactions like order books, which I explained. There's other things like private lending markets. So you can actually have proper, even over or under collateralized lending borrowing markets, which are completely private. Maybe you don't want to tell people that, okay, I've lent out 10 SOL and borrowed $1,000 against it, right? Maybe you don't want people to know what you're going to do with that $10,000 or $1,000 now. So you want not only your transactions to be private, but also the DeFi that you're interacting with to be private. As I said previously, with Manticore, we also enable private machine learning. So you can do end-to-end encrypted machine learning, not just inference or training, but completely end-to-end. So getting a bit more into the technical things, this is a high-level overview of how our architecture looks like. So basically, you have different parties have encrypted data. They send it, say, to the program that you've written on Solana. That program then calls the Arcium program. The Arcium programs basically runs an on-chain scheduler and an on-chain local fee market mempools for every single user's programs. Now, what that means is, since we are a stateless computation network only, and we don't do our own consensus, how do we order transactions? How do we make sure that they are done in a correct manner, right? So, for example, if any one of you has dealt with validator code or has an understanding of how blockchains work, basically, when you send a transaction to an RPC, that RPC calls the leader either directly or via some relayer, and the leader basically off-chain through communication collects all your transactions, puts them in a block, and then submits that block on the chain, and the other validators see that block, reach a consensus upon that block, and that is how ordering is done. Now, the problem with when doing this with Arcium is that since we don't want to do our own consensus and want to rely on Solana to do that, we can't do off-chain communication. If users directly send transactions off-chain to the Arcium nodes, then the problem will be, how do we determine the ordering? How do we determine how fees is paid? How do we we have to do our own consensus. So what we've built is that on chain, we run mempools for every single user program. Within those local mempools, your transaction gets added by the Arcium program. During the same instruction, we run on a scheduler, which basically sees, okay, I have XYZ transactions. Similar to how Solana does it, we check what accounts they are touching, those computations, what are their read inputs, what are their write inputs for every computation. We see those, we try to max parallelize them similar as to how Solana does it, and we make an ordering and put it into what we call the executing pool. So they get lined up in an execution pool, and execution pools are lined by slot numbers. So XY, 1 million slot, there are 3 transactions lined up, 1 million in one slot, there's 2 different transactions lined up, and so on. And depending on the slot number in the execution pool, the off-chain Arcium network nodes basically pick up all the transactions or all the computations for a given slot, fetch the data required for it, transform that data amongst themselves such that what's called as secret sharing in cryptography, and then compute on that data in parallel in all those computations, and then give you back the resulted output on chain. So what this leads to is a very efficient way to basically schedule stuff on chain. To go a bit more into the depth, any of you who might be thinking how this could be done would have realized that one of the major issues while doing something like this is that, let's say there's 1,000 transactions in the mempool. If I want to schedule those 1,000 transactions, it's super hard because there's a limit as to how much data I can pull into a single transaction. We have approximately 1 kilobyte limit of transaction data. So what data do I store in the mempool with respect to every single computation? So the data points that are stored is basically like, we basically need only the read and write account public keys, right? Now, the problem that arises is each account public key is 32 bytes. And if I want to input 32 into 1,000 transactions, that's 32,000. That's 32 times the limit of a single transaction. So what we basically do is we do two things. One, the mempool becomes a circular buffer per slot as well, such that at one point we're only ordering for a single slot. Secondly, we transform each public key from 32 bytes to 16 bytes. So 15 byte, we basically slice the public key from 32 to 15 bytes, and the 16th bit is basically defining whether the public key, whether the account is read only or write as well. And probabilistically, the chance of a collision while doing scheduling with this is about 1 in 2 to the power of 28 or something, which is super good because it's 1 into the power 2 to the 8, and the thing is 1 into 2 to the power 8. It's about 1 into 2 to the power 16 or something. And the thing is, 1 into 2 to the power 16 is really good. Right now, Solana can only handle about on-chain. It goes to max TPS of 1,500 or so. So 64,000 transactions is super hard to get in the near term. We'll hopefully get it with Alpenglow and the other updates. But until then, we're most likely secure against any attacks on that. So this probabilistic model works very well. Yeah. So now going a bit more into different privacy tech. So we have 3 options usually with shared state, which is MPC, FHE, TEs. TEs aren't an option for the use case that we're trying to explore. We want to do more secure, trust minimized computations. For that, FHE and MPC are our only options, as those are trusting math and not hardware. So they are less prone to supply chain attacks. There's FHE. FHE is good, but what we've built is Cerberus. Cerberus is our MPC model, which lets us IBRL. It's uses semi-homomorphic encryption, also known as or additive secret sharing. So we get rid of the expensive multiplications, which are usually a problem in MPC, and we replace them with correlated randomness, which helps us with selective disclosure, oblivious data structures, and more. So I'm running a bit on time, so yeah. So to wrap up, previous MPC approaches were honest majority. We are building dishonest majority. Thank you.